Welcome for this lesson. We are going to study probability and we are going to consider independent events on a tree diagram. We are given the probability of Akinyi, Kamau and Juma eat bullseye are 0.2, 0.3 and 0.15 respectively. If each plays once, show the possible outcomes on a tree diagram. So that is what the question says in part A. Very important to note that when we are given independent events like Akinyi's outcome, whether he hits the bullseye or not it doesn't affect the outcomes for Kamau, and that one doesn't affect the outcomes of Juma. We should note that even though Akinyi's outcomes, Kamau's outcomes, and Juma's outcomes are independent events, Akinyi eating the bullseye or missing the bullseye are mutually exclusive events, such that whatever happens affects the other. The probability of eating makes the probability of not eating for Akinyi become 0. Therefore, we should know that for mutually exclusive events, the probabilities must add up to 1, but for independent events like this one, it's not a must for the probability to add up to 1. Therefore, we're going to come up now with a tree diagram whereby we will first consider, because they are doing it independently, Akinyi beginning the game. If we assume Akinyi begins, then Akinyi can only do two things. Akinyi can either eat the bullseye or Akinyi fail to eat the bullseye. Probability Akinyi eating is 0.2, which means probability not eating will be 0.8. After Akinyi has played, if we assume the next player is Kamau, then Kamau can eat the bullseye or Kamau not eat the bullseye. Therefore, Kamau eating the bullseye is independent of either Akinyi had eat or not. So Kamau eating is 0.3, which means Kamau not hitting 0.7. So whether Akinyi had eat, we will get that. And even if Akinyi had lost, we will still have Kamau playing, and Kamau can still either hit or not hit, and this will be 0.3 and 0.7 respectively. After Kamau has played, we will have the last player, who is Juma. So Juma, on the same tree diagram, Juma can hit or Juma fail to hit, and Juma hitting is 0.15, which means not hitting is 0.85. So it will happen so regardless of what had happened before, because we are saying these are independent events. So Juma's hitting will remain 0.15 and not hitting 0.85. Even in this other case here, we will have Juma hitting, Juma not hitting, 0.15 and 0.85. And finally, we will have Juma and Juma not hitting, which is 0.15 and 0.85. After drawing a good tree diagram, it is very advisable you outline all the outcomes at the end of the tree diagram. Therefore, we have Akinyi, Kamau and Juma. Akinyi, Kamau and Juma, that is all eating. We have Akinyi, Kamau, Juma missing. Akinyi, Kamau, Juma failing. Akinyi, Kamau missing. Akinyi, Kamau missing, but Juma hitting. Akinyi, Kamau missing and Juma missing. Akinyi, Kamau missing, Juma missing. On the other side, we have Akinyi missing, but Kamau and Juma hitting. Akinyi missing, Kamau hitting, but Juma also misses. We have Akinyi missing and Kamau missing, but Juma alone eats. And finally, we have Akinyi, Kamau, and Juma all missing. So Akinyi, Kamau, and Juma all missing. So now, after analyzing the tree diagram like that, we can get into the response of the questions. We are taught to calculate probability that all hit the bull eye. So all hitting is the first case here. All hitting is the first case, whereby we get into part B, Roman 1, probability all hit is going to be probability Akinyi, Kamau, and Juma eating. And this is going to be 0.2, 0.3, and 0.15. This is going to give us 9 out of 1,000, or just as a decimal, 0.009. That is the probability that they are all going to eat. We can get to Roman 2, whereby we are told to find probability that only one eats the bull. Probability only one. So probability only one eats the bull's eye. It can be probability only one. It can be in this case whereby it is Akinyi alone, or in this case whereby it is Kamau alone, or in this case whereby it is Juma alone. So we just want probability that it is only one who was it. So it can be probability Akinyi hitting, but we have the others missing because we want probability just one, or probability Akinyi missing, Kamau hitting, and Juma misses, or probability Akinyi missing, Kamau missing, but we have Juma hitting. That is the possible cases where it is only one hitting the bull eye. Only one hitting the bull eye. So we will have, so we're going to have this case whereby it is 0.2 times 0.7 and 0.85, or means addition in probability. Akinyi losing, which is 0.8. After Akinyi loses, we will have Kamau alone winning, which is 0.3, and Juma losing, which is 0.85. And finally, Akinyi losing 0.8, Kamau losing 0.7, but this one called Juma alone hitting, which is 0.15. So this will give us 0.2 times 0.7 times 0.85. This is 0.119 plus 0.8 times 0.3 times 0.85. This is 0.204, and finally 0.8, 0.7, and 0.15, which is going to be 0.84 after a 0 here, sorry. So when we add up, we're going to get plus going to get 0.407. So that is the probability only one is going to hit. Then we have Roman 3, which talks of at most one misses the bull. At most one misses the bull. So we are going to consider, because we are told at most one misses, we are going to consider whereby the cases whereby they have won except only one. They have won except only one. So we will eliminate the cases where two people have missed. Where two people have missed. Because we want only one missing at most. So we have this case to be considered. This case. This case. This one has several people losing. We have two of them losing. This is going to be considered. This one is not going to be considered because it has more than one missing. Similar to this one and similar to this one, because we have more than one person missing. We have more than one person, more than one person, more than one person. So we want at most one person misses. At most one person. Therefore, where we have more than one person missing, then we eliminate. So we are going to consider now those four cases, whereby it is going to be the first case here, which is already calculated as 0.009, or this other case, which is 0.2 times 0.3 times 0.85, or the third case here, which is 0.2 times 0.7 times 0.15, or finally we have 0.8, 0.3 and 0.15. Therefore, those are the cases whereby the people getting are more than one. At most one misses. So when we are told at most one misses, then it means if the people missing are more than one, we eliminate that case. Therefore, now we can multiply, and here we will get 0.09 plus 0.2 times 0.3 times 0.85. This gives us 0.051 plus the other case is 0.2 times 0.7 times 0.15, 0.2 times 0.7 times 0.15, giving us 0.021, or finally 0.8 times 0.3 times 0.15, 0.036. So now we can add up all these cases, whereby it will be 0.009. Actually, this is 0.09